Alright guys, so today we're doing 1.3 notes day 1. These are our parent graphs, okay? So this is kind of the notes that will build the foundation for the rest of this class, because this class is a ton of graphing. So let's dive right in. Parent function. Constant. The constant function is y is equal to c. C is just some number, okay? Some real number. Can be any number. Let's use an example. Let's say this is the graph y equals 1. So then what we would do is we would go to 1, okay? And then that would just be our horizontal line. We've already talked about domain and range here. The domain is all real numbers. The range, I like to just write it as curly bracket. In this case, it's 1. The x-intercept, when we write intercepts, guys, they need to be in their coordinate pairs. So there is no x-intercept here, so not applicable. The y-intercept would be 0, 1. The max number of zeros. So when it says zeros, this means the number of times, so number of times we hit the x-axis. Okay, those would be our zeros. So in this case, it is 0 times. The end behavior. So this is kind of a new notation, but end behavior says what is it doing at the ends of this graph. So it's always written like this. As x goes to positive infinity, so positive infinity to the right, what is the y value going to? So the y value is just going to the value 1 because it stays there forever. Then we say as x is going to negative infinity, so as x is going to the left forever, where is our y value going? It's still going to 1, okay? So in both cases, as x goes to the right forever, y is going to 1. As x goes to the left forever, y is still going to 1. And that is our constant function. So the next function we have is a linear function. The general form for a linear function is y is equal to mx, okay? Where m is the slope, x is our variable. So then we can have any kind of equation that's linear. I guess we could put a plus b here, right? Y equals mx plus b. And then for this equation, we could just use the example y is equal to, I don't know, let's say 2x plus 1. That's a pretty easy one to graph. So then we'll go through here and graph. So y-intercept, up 2 to the right 1. I'm going to graph 1 point to the left as well. Then we can graph this. Should look something like this. Okay. Domain of this function, all real numbers. The range of this function, all real numbers. The x-intercept, in this case, I didn't pick one with a nice x-intercept. So, let's talk about how we would find the x-intercept. So whenever we're trying to find an x-intercept, that's where y is equal to 0. So we would just set 0 equal to our equation. So 2x plus 1 in this case. We subtract 1 from both sides. We get negative 1 is equal to 2x. Divide by 2, and we get x is equal to negative 1/2. Okay? So then negative 1/2, comma 0 is our x-intercept. Our y-intercept then is 0, comma 1. Max number of zeros for any linear function is 1. Okay, it can only go through the x-axis 1 time. The end behavior, so as x goes to positive infinity, so as it goes to the right, well, where's our y's going? Well, the y's are going up, so they're also going to positive infinity. As x goes to negative infinity, the y's are also going to negative infinity. Okay, and so that's our linear function. All right, so absolute value graph. Absolute value graph is going to be y equals the absolute value of x, okay? And so let's say we had the transformation form of the absolute value graph. It's going to be f of x is equal to a absolute value of x minus h plus k. All right, so that's our transformation form of the absolute value. So let's just graph the regular absolute value here. So regular absolute value, if you plug in 0, you get out 0. Okay, so when we're first doing this, it might be easy to build xy tables. So we plugged in 0, we got out 0. The next thing, if we plugged in 1 into the absolute value, we would still get 1. Okay. When we plug negative 1 into the absolute value, we get out a positive 1. So we go 1, 1, we go negative 1, 1. So the absolute value graph is actually looking like this. Okay. Whoop. Bam. So the domain for the absolute value function is all real numbers. Okay. The range of this is going to be from 0 to positive infinity. The x-intercept here is 0, 0. The y-intercept is 0, 0. The max number of zeros in this case is actually 2. Because if you think about it, if we would take this graph and then we shifted it down, well, now look at that. It crosses the x-axis twice, okay? So the max number of zeros that the absolute value graph can have is 2. And then the end behavior, as x goes to positive infinity, the y's are going to positive infinity, right? So as we go to the right forever, the graph is going up. As we go to negative infinity, f of x is going to negative infinity. Okay, so that's our absolute value graph. Next graph we're going to talk about is our quadratic graph. So the base form of the quadratic graph is y equals x squared. Transformation form is f of x is equal to a x minus h squared plus k. So that's our transformation form of our quadratic function. So again, XY table, guys, super helpful when building a graph for the very first time. So we plug in 1 into the equation, so y equals 1 squared. That would give us out 1. So when we plug in 1, we get out 1. I meant to plug in 0 as well. Y equals 0 squared is equal to 0. We plug in negative 1. Y equals to negative 1 squared is equal to positive 1. Okay. It might be helpful if you don't know what these graphs look like to plug in a couple more points. So let's do 2 and negative 2 just to be safe. So if we did negative 2 squared, that gives us 4. Positive 2 squared gives us 4. So both of these are 4. So we go 0, 0, 1, 1, negative 1, 1, positive 2, positive 4, negative 2, positive 4. Okay. So our quadratic looks like this. And then we can go through and fill out the domain and range. Domain, all real numbers again. Range, all real numbers. X-intercept, 0, 0. Y-intercept, 0, 0. The max number of zeros, again, in this case is 2, because if we would shift this graph down, we would cross the x-axis at 2 spots. Okay, so the max number is 2. How about the min number of this one, right? The minimum number of zeros would be 0. And if we went back to the absolute value, the minimum number of zeros here is also 0. Okay, so that might be something that is pretty important. That might come up to haunt us some days. End behavior, as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. If the f of x thing is still screwing you up, guys, just use y for now, okay? But know that when I say f of x, I'm talking about the y values. All right, cubic function. Cubic function is y equals x cubed. Transformation form of the cubic function is f of x equals a x minus h cubed plus k. So hopefully you're starting to pick up on the pattern for the transformation form. It doesn't really change much after that, okay? All right, let's build our xy table for the cubic function. So we have x's, we have y's. Just build the table right on this line. Plug in 0, you get out 0. You plug in 1, you would get out 1, because 1 cubed is still 1. You plug in negative 1 cubed, you get out negative 1 this time. You plug in 2, you cube it, you get out 8. You plug in negative 2 and you cube that, you get out negative 8. So 2 gives us 8. Or wait, yeah, 2, yeah. Negative 2 also gives us 8. So let's graph that. 0, 0, 1, 1, negative 1, negative 1, positive 2, positive 8, 1, 2, 3, 4, 5, 6, 7, 8. And then negative 8 would be right here. And then to graph this one, we're going to come through that point, come up through, Bada bing, bada boom. Graph of the x cubed, or the cubic function. Domain, all real numbers. Range, all real numbers. X-intercept here is 0, 0. Y-intercept here is 0, 0. The max number of zeros for our cubic function is 1. Okay, the minimum number of zeros, though, is also 1. We're never going to not be able to go through the x-axis with a cubic function. The end behavior, as x goes to positive infinity, f of x is going to positive infinity. As x goes to negative infinity, f of x also goes to negative infinity. I just realized writing this range right here that I messed up the quadratic function, right? The quadratic function should not have a range that's all real numbers. It's from 0 to infinity, just like the absolute value. So I apologize for that, guys. It's a quick little fix, though. Hopefully you caught it on the first time when I was going through there. I was just going too quick for myself. All right, square root function. Square root function is y is equal to the square root of x, okay? Transformation form, f of x is equal to a square root of x minus h, and then plus k is outside of the square root. So if we're graphing this function, when we do our xy table, the square root function, we have to pick numbers that are nice for a square root. So in this case, 0 is nice because that gives us out 0. 1 is a nice number because the square root of 1 is just 1. 2 is not a nice number because the square root of 2 is some decimal. Square root of 3, same thing. Square root of 4, though, is a nice number because then we get 2. So I'm going to use 4 as my next one and get out a 2. We cannot plug in negative square root numbers. We haven't learned what those are yet, okay? So we'll get there soon, though. So 0, 0, 1, 1, and then 4, 2. So it looks like this. And then our graph should look like half of a parabola on its side. Domain here, we start at 0. We go to positive infinity. Range, we start at 0, and we're going to positive infinity. X-intercept is 0, 0. Y-intercept is 0, 0. The max number of zeros here is 1. We also have a minimum number of zeros here, which is 0. Okay. Our end behavior, so as x goes to positive infinity, so as we go to the right, okay, f of x is also going to positive infinity. Now this end behavior is a little bit weird, okay? As x is going to negative infinity, so as x is going to the left on the graph, the y value that we're going to is right here. So we're going to a y value of 0. Okay, so I know that can be a little confusing, and please, please, please ask me questions on that one, okay? So last little graph here, we have the cube root function. This is y is equal to the cube root of x. Transformation form, f of x is equal to a cube root of x minus h, and then plus k is outside of the cube root. Cube root is something that you may not have seen before, so let's talk about how it operates, right? It's the opposite of our cubes. So whatever we're picking to throw in here, we want to use the cubes for. So 0 is a good one always. We get out 0. 1 times 1 times 1 is equal to 1. So if we put in 1 into the cube root function, we would get out 1. Okay. The next best one to pick, 2 times 2 times 2, gives us 8. So then if we're plugging in 8 into x, we would get out 2. With the cube root function, we can actually do negative numbers as well, right? So the cube root of negative 8 would give us out negative 2. And the cube root of negative 1 would give us out positive 1. So negative 8 gives us negative 2. Negative 1 gives us negative 1. Okay? And that's because negative 2 times negative 2 times negative 2 is negative 8. Okay? 3 negatives in a row will still make a negative. So this graph, 0, 0, 1, 1, negative 1, 1, or negative 1, negative 1, sorry. And then positive 8, which is here, positive 2, negative 8, negative 2. Okay? So what this graph should look like is it should look like the cube root graph flipped on its side. As we go through the domain and range here, the domain, all real numbers. Range, is also all real numbers. The x-intercept is 0, 0. The y-intercept is 0, 0. The max number of zeros here is 1. The minimum number of zeros here is still 1. Okay? And behavior, as x goes to positive infinity, y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. Okay? So those are all of our parent functions that we're going to work with this year. As always, guys, if you have any questions, please ask me in class. That's what I'm here for. I hope you guys have a great rest of your day.